Hello, everyone, and welcome to Control Station's webinar series, Inside the Red Zone. My name is John Stevens, Control Station's Director of Partner Development. Today's session topic is ensuring continuously optimized control system performance. If you could, please place your phones on mute for the duration of today's session and submit any questions that you may have using the text chat function. As time permits, we will address questions at the conclusion of the web seminar. We're fortunate to be joined by Danny Aspefik of Eldor. Danny started his career as a process engineer in 2019 and has been working at Eldor focused on process control and alarm systems. Danny received his master's degree in chemical engineering from the Norwegian University of Science and Technology in 2018. Over the next 20 minutes, Danny will present on the benefits and the process of manually tuning PID controllers. So without further introduction, let's get inside the red zone. Danny, the floor is yours.
Thank you. So I will start by talking about the benefits of good process control. Later on, I'll move on to talk about how to manually tune a PID controller. And this is because it is so common to find poorly tuned PID controllers in the industry. After that, I'll move on to show how monitoring, or talk about how monitoring the process performance can help you achieve an optimized process control system. So when a chemical process is designed, the design is based on a steady state, but during the operation, the plant is in need of a system to counteract the disturbances and keep it close to the design specification. And this is the task of the process control system and of course the operator. The goal is always to operate the plant as close to optimal as possible. And when the control system works, the control room operators are able to maintain normal production and handle any possible disturbances. A little bit about disturbances. Disturbances can lead to non-optimal production and are normally variables that are not controlled and can cause changes in the process. Disturbances can be changes in the feed, for example, temperature, composition of flow. Other disturbances can be process dynamics, changes made by an operator, or failure of equipment, just to mention a few. Through tuning, disturbances can be minimized but not removed. The best way to remove a disturbance from the PID is to find the disturbance and fix it at source. PID controllers are the most widely used controller in the industry, and it is a known fact that many of these controllers are poorly tuned, and some have never been tuned at all. It's not uncommon to observe loops with self-induced oscillations because of excessive integral action, or finding a cascade controller or cascade loop where the outer loop is tuned much faster than the inner loop. So on the picture here to the right, in the first part of it, you can see a typical controller with poor parameters. Running the process like this without a set of well-tuned parameters may work just fine, but the process is less profitable. Providing a set of optimized parameters helps utilize the full potential of the plant and typically increases the production throughput, the production yield, and lowers the energy consumption, the need for maintenance, in addition to ensuring a more consistent quality of the product. I just want to give an example of how badly poor parameters can affect your production. This example I have from my professor at NTNU. In this example, or this is a real life example, the production facility had problems with oscillations in a distillation column, and this led to unplanned shutdowns. For a long time, they thought there was a problem with the distillation column, and they took several approaches to fix the problem within the distillation column, but nothing worked. When they analyzed the system closer, looking at the entire process, considered the process dynamics, they discovered that there was a level controller, that there was a reboiler in a column upstream of the distillation column, and the level in this reboiler was oscillating. The oscillating level in the reboiler caused fluctuations in the feed stream into the distillation column, And this in turn caused oscillations in the distillation column. They investigated the tuning parameters for this level controller, and they found that it was caused by poor parameters. They tuned this controller, and the problem was solved. Tuning this one controller meant that they increased uptime, production, and reduced the wear and tear on the equipment. So what do I mean by optimizing a process control system? Generally, it is difficult to define the optimality of a controller, as there are many important aspects to take into consideration, such as set point response, disturbance rejection, robustness, input usage, and noise sensitivity. So altogether, process optimization is about tuning the loops in a way that allows the entire process to operate as close to the operating constraint as possible. So in this picture here to the right, it is this is really what process optimization are. You have a set of poor parameters, and you need to set the set point further away from the operating constraint. In the midsection, a set of well-tuned parameter has been provided for the controller. The small peaks you can see here are likely caused by disturbances and cannot be fixed by tuning. But because these variations are so much smaller than they originally were in the first part, you can move the set point closer to the operating constraint. And by operating closer to the operating constraint, you get the benefits of an optimized performance, meaning you reduce the energy consumption. Typically, this reduction is between 5 and 15%. You get a more consistent product quality. It's easier to operate, and it reduces the wear and tear on the equipment. Moving on to how to manually tune a PID controller. I'm saying PID controller, but what I really mean is PI controller. About 90% of all controllers in the industry are only the PI. So, as I mentioned, there are many poorly tuned controllers in the industry, and this is why we are looking at this. The procedure that is listed here on the right is a procedure that the control station is using when they are tuning with Control Station's Loop Pro. But I think it's a good procedure, and it can also be applied to manual tuning. So the first step to think about when we tune is good process is simple. Safety is paramount to everything else. Second, impact. What is this loop controlling? Where does it fit in the overall process? Management. What performance do the operators want? What performance do the management want, or the customer? And if it's not possible to achieve this performance, it is our job to explain why this performance cannot be achieved. Profit or optimization, I can say. What are the economic factors associated with this loop? Energy consumption, valve wear and tear, and throughput. And lastly, it's longevity and equipment. They're more or less the same. The more aggressive parameters you provide with the controller, the more wear and tear it can cause. So when you tune, the second part of this recipe is doing the step test. The first thing I should mention with the step test is the process noise. It is very important that the step test is clearly dominating the noise band. And on the right, in the picture to the right, you can clearly see a step test that is dominating the noise band, what it looks like. So the step test that we prefer is a double doublet. It's not exactly what I'm displaying here. A double doublet is going half up, one big down, and then instead of this half up, you go one big up, and then you go half down again. We prefer the double doublet test because it gives you process informations information in both directions. A test like this is also good for detecting if something is wrong. If you don't get the same response for the identical steps, you know that something is wrong and you need to investigate. Another thing that is important to mention is that the step test should cover the range of the process which you want to control. Let's say in this figure that you only want to control around the 25%. Then it's fine to only do one step test within that range. But if you want to control the entire range, you need to do the step test in the entire range. And you may encounter this issue, which is depicted in this figure, where equal steps in the controller output is not giving the same response in the process variable, depending on where it is being operated. So if you get a response like this, there are two options. You can either do a big step test and use the same parameters for the entire range. This might not yield a good set of parameters. So the alternatively, you can do several step tests as depicted and find different parameters for different areas of the range you want to control. And this is called gain scheduling. Since most controllers in the industry are PI controllers, I'm only showing how to tune from a process assumed to be a first order plus time delay process, which in turn will yield a PI controller. On the left, you can see tuning rules developed by a professor at NTNU, Sigurd Skogestad. So how do we tune from a step test? In this figure to the right, I have tried to draw an example of how to do it. We find the steepest slope and use the slope to calculate K prime. After that, we extrapolate the tangent down so it crosses the line where the process is starting, and from where the step was done in the controller output, and up to the point where the extrapolated line is crossing. That is our time delay. We insert these values into the SIMC rules, and we find our controller gain and time constant. For the tau c, we usually select it equal to the time delay, but it's ultimately an engineering decision. This is like a tuning variable, or this is a tuning variable. The formula displayed in the lower left corner in blue is developed by Finn Haugen, or is SIMC further developed by Finn Haugen, and it gives a faster set point response, but it is less robust than the original SIMC rules. So step 4 is tuning the controller. You need to convert the controller gain and time constant to fit with the controller on your facility. The information needed should be in the controller manual. Next, you test your tuning and you document the work. I showed how a controller can be tuned manually. I did this not only so you would learn how to tune a controller manually, but also to demonstrate how valuable the process data that you already have available is. Monitoring the process data is key in ensuring the plant performance is satisfactory. A little bit of what a monitoring tool can do. A monitoring tool can calculate many different metrics and display them in a way so that they are easy to understand. Looking at the metrics and combining what they are saying, the metrics can be used to decipher trends in the process data that are connected with a variety of challenges, ranging from mechanical and PID controller tuning issues to more complicated problems with the process. So a little bit about detecting mechanical issues. It is possible to pick up signs that the equipment, such as a valve or a compressor or a pump or some other asset, is about to fail before it impacts the production. You can pick up tuning issues. As I mentioned with the example from my professor, where a poorly tuned controller can have a profound effect on the plant-wide performance. And identifying these tuning issues can be challenging. Monitoring the loops makes it easy to assess the effectiveness of each PID controller and the tuning relative to the associated process performance. It can also help you detect process issues. At most production facilities, change is constant, and some changes impact a process ability to meet its objective. From frequent set point changes to regular mechanical maintenance, monitoring solutions will help you understand which changes affect a given process and its ability to perform as designed. So we went through a method for tuning a controller manually. It is critical that the step test is performed in a range that you want to operate in and that it dominates the noise band. And lastly, I talked about monitoring. I should mention that installing the monitoring tool alone will not help you optimize the plant's performance if you do not have trained and dedicated personnel that are following up the tool, investigating potential issues, and dedicated to improve and sustain the plant performance.
Great presentation, Danny. Thank you. I wanted to kind of open the floor for anybody that may have some questions. Again, you have the chat function within Zoom. If you feel more comfortable, maybe typing those in, I'd be happy to sort of read some of those off as time permits. Maybe as some of you guys are doing that, there were a few questions, Danny, that I see that were submitted prior to the presentation. I figured I might start with, and again, anybody, if you have any, feel free to add those to the chat. Danny, the first question, how does the method that you described apply to level controllers that don't settle?
So when using for this method that I am saying, that I showed, it is generally not necessary to run the experiment for longer than 10 times the effective delay. Because at this time, you can approximate it as an integrating process. I don't want to go further into details about it's very technical about why you can assume that, make that assumption.
Okay. So this next question, I know just myself, this is definitely one that customers, engineers just in general, when going out and tuning, it's definitely one of the big questions. You recommended a number of that a step test needs to dominate the noise within the process. Can you be more specific and give people a sense of how big of a test is needed?
So what we have discussed is that as large as possible is the is the more politically correct answer, but 3 to 4 times the noise band, at least it should be.
Okay.
3 to 4 times the noise band.
That's a good rule of thumb. I'm not seeing any other questions come through, but again, post this presentation, we'd be happy to field any of those outside of this as well, whether Danny directly, or if you were to contact Control Station, we could push that back to Danny as well. But it is all we have time for today. Danny, really good timing. Right, we fit that 20 minutes in perfectly. Once again, I want to thank everybody for joining us. Just so you know, the presentation is going to be published shortly and will be accessible on controlstation.com. So if you want to view this later or pass this to colleagues, we're continuing to host these. And so we'd always open and be welcome to having you guys join us again. And we really appreciate, Danny, your time and everybody else's time this morning in joining this. So everybody have a great rest of the day, and thank you.